Hello! Hey guys, welcome to Isomers Chiral, Achiral, and Meso made easy. This is going to be a three-part series, and we're going to mainly focus on clarifying these 5 things down here. Enantiomers, Diastereomers, Achiral, Chiral, and Meso. In part 1, we're going to go through this problem, where you have a molecule and you're asked to draw an enantiomer, an Achiral Diastereomer, a Pyro Diastereomer, and well, that's basically it. And then in part 2, we are going to tackle this problem here, where you have 4 molecules, and then we have a little checklist here, and we're going to see if these molecules are achiral, have an enantiomer, have at least one chiral diastereomer, contains at least one chiral center, and has a mesodiastereomer. I know that's a lot of vocabulary, but we're going to clear that all up. And then in part 3, we're going to jump over here and do this. I think this is probably the hardest problem that you can do, or the hardest type of problem you can do, involving isomers and isomers. So we're not going to do this exact problem, but we'll do something similar, and that's in part 3. So be sure to check out all 3 parts and get this concept cleared up. Alright, so first off, here's molecule A. Why don't you try it out first? Can you try giving me what an enantiomer will look like, a chiral diastereomer and a chiral diastereomer, and we'll come back and tackle it together. Alright, so hit pause. See ya. Okay, did you guys get an enantiomer and these guys? Well, as you see, there's a whole bunch of words that we have to define in order to do these problems. But just first off, constitution isomers, they're 2 molecules that have the same formula but different bonding. So I'll give you an example, why not? Right here, this is that, and then its constitution isomer would look like this. Same formula, 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons, bromine, bromine, and then hydrogens, same number. The main focus of this video will not be constitution isomers, and I think they only pop up in part 3, but I already have a video out called Isomers Made Easy that does go over a few examples, so if you want to check that out, I'll put the link right here in the cards. Alright, so yeah. There's a lot, so I'll define them as we get to it in the problem, but really important, I think it's good if you guys keep in mind that these 3 things right here, constitutional isomers, enantiomers, and diastereomers, they're just ways to define relationships between different molecules, and achiral, chiral, meso are just ways to describe a single molecule, typically. Okay? So here we go. First part, we need to draw an enantiomer of A. So what's an enantiomer? You might be used to hearing the definition, it's the mirror image of a molecule that's not superimposable, and I like to think of it as just a different molecule compared to the original one that has the same formula, same connectivity, but the only difference is the wedging and dashing. And the difference is that all the wedges and dashes have flipped. So all we really need to do for this problem is turn these wedges here and this dash into the opposite wedge or dash. So here we go. Same formula, same bonding. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then we're going to dash this too. Chlorine. And we're going to wedge this chlorine right here. Okay, and I'll switch out that Br I drew with the OH. My bad on that. Alright, so an enantiomer is a different molecule that has the same formula, same connectivity, all the wedges and dashes have flipped, and you have to make sure that it's not identical to the original. So I like to think of it that way instead of not superimposable, because it's an extra word that you don't have to worry about. But basically you need to check if this molecule is actually the original molecule. And so right now it's not, and you have to check to see what if you flip it, what if you flip the entire molecule over like this, or over like that, or if you rotate it, can it become the original molecule? Because if it can, then it's just the original molecule. It's not a new enantiomer. So I'll show you how you do it. So you turn this, pick it up and flip it. What will you get? You will get wedge in here, wedging here. This wedge that's out gets flipped over here, and it's going to be going in. So you're going to get actually a dashed CL here, and then this dash CL that's here going in is going to get flipped out. So you're going to get a wedge CL here. And so yeah, by flipping this, you create this, and this is not the original molecule. So therefore, you just created an enantiomer of molecule A. Alright. Okay, so now let me just erase all this because we don't need that. Next part, we need to create an achiral diastereomer of A. So that's two vocabs. First, let's break it down. What's achiral? Achiral is just symmetry. There has to be a plane of symmetry somewhere in your molecule. And then diastereomer, that's the next stereoisomer that you have to learn. It is a new molecule that has the same formula, same connectivity, but different wedging and dashing, or different E or Z if there's a double bond in your molecule. So, also very important, you can flip some of the wedges and dashes, but you just can't flip all of them. And why is that? Well, if you flip all of them, then you just created your enantiomer once again. Okay? So just remember, flip one or more, but not all. So here we go. How can we change the wedging and dashing here, one or more, and make it symmetrical at the same time? So there's actually quite a few ways to do that. And one way of doing that is by flipping this CL. So I'll show you. If you turn this into a dash, then the molecule becomes symmetrical. Alright, so here we go. And that is an achiral diastereomer of molecule A. Alright, there's actually a few more achiral diastereomers that you can make, so why don't you try that out? I'll tell you what they are. If you turn this into a wedge, then there's a plane of symmetry, just like this one, and that's an achiral diastereomer. If you flip, if you turn this into a dash, and then keep these wedges, keep that as a wedge, and then turn this one into a wedge, well then, that's also an achiral diastereomer, another plane of symmetry. So there's really quite a few ways you can play with this molecule and its wedging and dashing to create an achiral diastereomer. Alright, and next we're going to move on to chiral diastereomers of A. So, what does chiral mean? No symmetry. Oh, and also, meso mentioned earlier, we won't see in this video, it'll be in part 2, but meso just means that your molecule has symmetry, and there's at least 2 chiral centers. So carbons with 4 different groups attached to it. Alright, so here, chiral diastereomers. So what can we do to this in terms of flipping, wedging, dashing to make a molecule that's not symmetrical? Well, you can just flip this into a dash. And here we go. See how there's no symmetry now? And you change the wedging and dashing, so that is a diastereomer, and it is also chiral. There you go. There's same thing, there's quite a few combos you could do. You could have flipped just that into a dash. You could have flipped this into a dash and that into a dash. That would have also been chiral as well, no symmetry. Or you could have flipped all 3 of these into dashes, and that would also be chiral diastereomers of A. Alright, so hopefully this video cleared up enantiomers and diastereomers a little bit for you guys, and I just really want to show you guys how to think about them in terms of just wedging and dashing, and not so much in terms of mirror images, superimposable, and however else you can tell. Okay, so yeah, there we go. That is part 1, and if you want to see part 2, where we do the harder problem, be sure to check that out. I'll include a link in the cards right here. And yeah, if you have any questions, feel free to ask me down below. If you like this video, make sure you like it down there. And I'll see you guys in part 2 then. Bye.